It's a pleasure to introduce our next speaker, Professor Ganna Kudryavtseva from Ljubljana University. The title of the talk, Relating Ample and Biample Topological Categories with Boolean Restriction and Range Semigroups. Please.
Thank you very much for the introduction. Do you hear me?
Yes, we hear you.
Okay, perfect. Let me share my slides. Okay. Do you see my slides?
Yes, very good.
Okay, perfect. So I'm happy to be here to give a talk at this conference. Thank you for the organizers for the invitation and for the opportunity to present my work here. And the conference is indeed wonderful, and I admire organizers for all their work, especially during these hard times. So let's go on to my talk. So today I'm going to speak about connection between ample and biample topological category with Boolean restriction and range semigroups. And let me start from introducing objects which inspired this work, actually inverse semigroups, and after that they are non-regular generalizations. So semigroup S is regular if for each element of this semigroup there is another element satisfying ABA is A and BAB is B, and the element B is called an inverse of A. It may happen that one element has many inverses, but in the case when each element has a unique inverse denoted by A to minus 1, semigroup is called inverse semigroup. Unlike groups, inverse semigroups can contain many idempotents, and E of S is notation for the set of idempotents, and it can be proved that semigroup S is inverse if and only if it's regular and its idempotents commute. Consequently, they form an idempotent commutative subsemigroup. Idempotents can be looked at as semi-lattices with respect to the order E is below F, if and only if EF equals FE equals to E, and then the product is just the greatest upper bound of E and F. So commutative idempotent semigroups can be equivalently viewed as semi-lattices. Natural partial order is given by restricting one element to another with idempotent. And every group is an inverse semigroup, and every semi-lattice is an inverse semigroup. So these are first examples. Now, symmetric inverse monoid consists of all bijective maps between subsets of a set X. Idempotents of IX are identity maps on subsets of X, and the natural partial order is given by restriction of B to the domain of A. Now, partial transformation monoid consists of all partially defined maps which are not necessarily injective. There is even bigger monoid of binary relations on set X. We have these inclusions. PTX, partial transformation monoid, is regular but is not inverse. Binary relation monoid is even not regular in general. Well, now I go on to non-regular generalizations of inverse semigroups. So Ehresmann and restriction semigroups. So Ehresmann semigroup, it's an algebra which is a semigroup with respect to multiplication and has a unary operation plus such that the axioms which you see on your screen are satisfied, and co-Ehresmann semigroups are defined dually. Bi-Ehresmann semigroup combines both of the definitions, so it is Ehresmann and co-Ehresmann, and in addition, pluses and stars of elements are related as you see on the screen. Axioms imply that if you apply star to an element 2 times, you get the start element, and all stars of elements are idempotents. So these elements with stars will be called projections. In inverse semigroups, projections coincide with idempotents. And very soon we will see examples, but before examples, let me introduce restriction and bi-restriction semigroup. So restriction semigroup is an Ehresmann semigroup such that additional identity holds. And so this y star is a projection, and when you multiply projection with x, you can just move this projection to the right-hand side of x. So it's x times yx star. But remember, yx star is the same thing as y star x star. So you just multiply x from the right by the star of the whole element, which you see on the left. Co-restriction semigroups are defined dually. Bi-restriction semigroup combines both these definitions. So it's restriction and co-restriction. So set of all stars of elements, as I already said, is called set of projections, and axioms directly imply that this is a semi-lattice. You can think about this as analog of semi-lattice of idempotence in an inverse semigroup. In bi-Ehresmann and bi-restriction semigroup, set of all stars coincides with set of all pluses due to the axiom I showed you on the previous screen. And now I want to introduce range semigroups. It is bi-Ehresmann semigroup, which is restriction, but not necessarily co-restriction. And this happens precisely for the semigroup PTX of partial self-maps of X. Okay, so because maps are not in general bijective, the semigroup is not co-restriction. The axiom for co-restriction is not satisfied. Okay, so range semigroups, this name comes from category theory because range categories have been studied in category theory for quite a long time. Restriction and bi-restriction semigroups generalize monoids and inverse semigroups at the same time. If S is an inverse semigroup, we define plus of element is just range idempotent and A star is domain idempotent. And so if S is a monoid, we can put pluses and stars of all elements to be equal to 1. And from this example, you see that monoid can have more idempotence than just 1. And this idempotence, if we define operations like this, are not projections. So if you consider monoid of binary relations, we can define star of a relation as its domain relation, plus of a relation as its range relation. And with respect to these operations, we obtain a bi-Ehresmann monoid, and this is our prototypical example. PTX, as I already said, is a range monoid, and IX is a bi-restriction monoid. Of course, it's also an inverse monoid. A star operation is sometimes called support operation, and plus operation is called co-support operation. For these semigroups, we have Cayley type theorems. Every inverse semigroup can be embedded into some I of X, and so does every restriction semigroup. It embeds into some partial transformation monoid. That's why these examples, I of S and PT of X, play similar role as symmetric group plays in group theory. Well, if we want to see some more easy examples, let us consider semigroup of all upper triangular Rook matrices. Recall that inverse semigroups can be represented as Rook matrices, and if we consider only upper triangular matrices, we obtain a semigroup which is not inverse, and moreover, its invertible elements are just idempotents, but it's by restriction because it contains all idempotents of symmetric inverse monoid. Now, let me introduce a notion of partial isomorphism. So if you have restriction semigroup, so you have multiplication and star operations, it may happen that for element S, there is another element S prime, such that S prime X equals S star and S prime equal S prime star. Yes, and in this case, we say that S prime is partial inverse of S, and this was introduced by Jackson and Stokes and by Cockett, Guo, and Hofstrom. So if S is a partial isomorphism, then its partial inverse is unique and is also a partial isomorphism. If S is an inverse semigroup, then every element S is a partial isomorphism, and its true inverse coincides with its inverse. And in any restriction semigroup, the set of partial isomorphisms is closed with respect to the multiplication and is an inverse subsemigroup. And it can be looked at as an analog of the group of units of a monoid. Now let's go on to bideterministic elements. These elements can be thought about as abstract analogs of partial bijections. So if we have a bi-Ehresmann semigroup, element is called deterministic if for all projections E times A equals A times EA star. So when projection can be moved on the right of the element. This can be done in restriction semigroups, but not always in Ehresmann semigroups. And this can be done precisely for deterministic elements. Codeterministic elements are defined similarly. And D of S denotes the set of all bideterministic elements, that is, elements which are both deterministic and codeterministic. So deterministic elements form a 2-1-1 subalgebra of S, so closed with respect to multiplication plus and star, and it is a bi-restriction semigroup. And inf of S is contained in the D of S. For example, if S is a partial transformation monoid, then D of S coincides with in of S and its symmetric inverse monoid. But the inclusion in 2 can be strict because for upper triangular Rook matrices, all its elements are bideterministic, but partial isomorphisms, those which have inverses, are only idempotents. Well, and compatibility and bicompatibility. So if we have restriction semigroup, that similarly to inverse semigroups, we can define natural partial order, and PT of X is just restriction of partial maps. And we define compatibility relation whenever elements A and B are agreed on intersection of their domains. So co-compatible elements are defined similarly, and combining these two, we get a definition of bicompatible elements. If you have a bi-restriction semigroup, then being bicompatible is equivalent to be compatible and co-compatible, and for inverse semigroup, it's equivalent that A and B are compatible, and A minus 1, sorry, here is a typo, is compatible with B minus 1. Okay, so it was a short crash course to inverse semigroups and their non-regular generalizations. And now let me go on to present results which are more closely connected with the topic of my talk. So Boolean inverse semigroups. Symmetric inverse monoid is an example of a Boolean inverse monoid. Why? Because observe that its idempotents form a unital Boolean algebra. It's just power set of X, right? Some special property which not all inverse semigroups have this property, right? But IFS has this property, and joins of compatible elements exist. So whenever you have two partial bijections which are eligible to have a join, which nicely match, then the join indeed exists in symmetric inverse monoid. And that's precisely the definition of a Boolean inverse monoid. Boolean inverse semigroups give rise to the groupoids of ultrafilters from which they can be reconstructed. And this generalizes classical stone duality between Boolean algebras and generalized Boolean algebras and locally compact stone spaces, and leads to non-commutative stone dualities. So here I state some papers where this was developed. First paper is due to Pedro Rezende. He did this duality actually in the point-free setting, but only for objects. He didn't consider morphisms. So Mark Lawson did it for Boolean inverse semigroups with MIDS. Then he continued this work in his next paper, in fact, in a series of papers, and then in a joint work with Daniel Lenz, he established dualities for pseudogroups whose idempotents form a frame, and then the derived consequences for Boolean inverse semigroups, and they considered several kinds of morphisms. Well, and now one comes to a question, actually, if this can be further generalized. And first question is actually, are the inverses important? So can we drop inverses? Do these results admit generalizations to, say, restriction or Ehresmann semigroups, etc.? Okay, and we considered these questions jointly with Mark Lawson in our paper published in 2017, and we found out that there is generalization of these non-commutative stone dualities to Boolean bi-restriction semigroups. Okay, so you don't have inverses, you only have plus and star operations, and they are dual to biample categories. This was further generalized by Cockett and Gardner to wider setting, which implies duality for Boolean restriction semigroups. So those who have only multiplication and star operation but don't have plus operation, and these are dual to ample categories. Okay. And the starting point of my work was actually the question that restriction semigroups possess multiplication and star operation, but they don't possess plus operation. Whereas they are dual to categories, objects which naturally possess both domain and range map. And I wondered what is the role of the range map for the Boolean restriction semigroup, and if some properties of the range map are reflected in the properties of restriction semigroup. Another question was if we can drop the requirement that we're working with monoids, and if these results can be extended to semigroup setting and to locally compact setting, because the role of one was very important in the work of Cockett and Gardner, and it was unclear how to proceed without one. So I would also mention that equivalence from my work with Lawson does not follow from the results of Cockett and Gardner, since their theory is developed for the case of one unary operation on the algebraic side, whereas in our work with Lawson we have two unary operations. So in this talk we present results which extend the above equivalences to restriction semigroups with local units, so we don't need one anymore, and locally compact spaces of units of respective categories. And we explore when restriction semigroups can be equipped with a compatible co-support operation. This generalizes and provides a common framework for both Kudryavtseva-Lawson and Cockett-Gardner results. And these results were recently published in my paper, which is entitled the same as this talk. So let me precisely define the algebraic objects I'm working with. So Boolean restriction semigroups. So we have a restriction semigroup. We assume that it has a zero element, which is a projection. And we assume that the following three conditions hold. So whenever we have two compatible elements, they have a join in our semigroup. Projections form a generalized Boolean algebra, that is Boolean algebra without top element. And instead of complement, there is difference operation. And we have a right distributivity. Left distributivity holds automatically, but right distributivity must be imposed. I also introduce the notion of a pre-Boolean semigroup, where I relax condition 1 by the following condition. For any two elements which have a common upper bound in S, their join exists. And actually, this pre-Boolean case will be needed for us to establish a junction between pre-Boolean restriction semigroups and ample categories. And this junction will imply equivalences for both restriction and bi-restriction cases. So this notion subsumes both Boolean restriction and Boolean bi-restriction semigroups. So we say that S has local units if for each S in S there is projection such that E times S equals to S. If S is a range semigroup, it holds automatically, just take S plus, but in the absence of plus we impose this. Of course, each monoid satisfies this condition, it has local units. Symmetric inverse monoid is pre-Boolean restriction semigroup and Boolean bi-restriction semigroup, but not Boolean restriction. So if you take two elements which are compatible but not bicompatible, they may not have upper bound and no join, but it is pre-Boolean. Now I introduce topological objects. Topological category I put precise definition here. It's two sets, C1, C0, and maps, structure maps, U, D, R, M, unit map, domain, range, and multiplication maps. And very shortly, it can be defined as internal category in the category of topological spaces. Topological groupoid is defined similarly, internal groupoid in the category of topological spaces. And so C1 and C0 are topological spaces and all structure maps are continuous. So this is precisely what this means. We call a topological category étal if the domain map is a local homeomorphism. And we call it biétal if both domain and range maps are local homeomorphisms. Note that for topological groupoids, étal and biétal are equivalent due to presence of inversion map. But for categories, it's not the case. An open subset is called a slice if the restriction of the domain map to the set is injective. And slice and a co-slice simultaneously is a bislice. Well, two nice properties. If you have a étal topological category, then the unit map is open. It's not difficult to prove, and there is similar property for étal groupoid. But Tristan Bayes has contributed very important observation that the multiplication map is open. So in an étal topological category, the multiplication map is not only continuous, but it's open. Well, and the collection of all slices of an étal category form a basis of topology of the topology on C1. The collection of all bislices of a biétal category similarly forms a basis of the topology on C1. Okay, now from an étal category, we can construct a restriction monoid simply by taking slices. Actually, slices, due to openness of the multiplication map, product of slices is a slice, and star operation is just identity on the domain of a slice. And everything works nicely, and we get a restriction semigroup, which we denote by C op. But for my purposes, I need to restrict my attention to those categories whose space of identities is locally compact stone space. An étal category will be called ample if compact slices form a base of the topology on C1, and similarly, biétal category will be called biample if compact bislices form basis of the topology on C1, and one can easily show that étal category is ample if and only if C0 is a locally compact stone space. Okay. Now, I define strongly ample categories. Strongly ample means that the range map is open. In general, it's only continuous, but whenever it's open, I call it strongly ample. Denote the set of all compact slices of an ample category by SA title. Proposition, the set by CA, sorry, and set of compact bislices by CA title. And so the set of all compact slices forms a restriction, is closed with respect to the multiplication and the domain operation, and forms a 2-1 subalgebra of our previous restriction monoid. It is a monoid if and only if C0 is a compact space. So if C is an ample category, then CA is a Boolean restriction semigroup with local units. And if it's strongly ample, that it's a range semigroup. The R of slice can be defined as plus of this element in your semigroup. And if C is biample, CA is an étal range semigroup. I don't define this notion due to the lack of time. Now the other way around. Now we start from a Boolean restriction semigroup with local units, and we want to define its category. And here we follow the usual construction, how to construct tight groupoid of an inverse semigroup. But of course, construction needs modification because we cannot conjugate elements as it's possible in the case of inverse semigroups. So the action of our restriction monoid on the space of characters of its projection similarities is now given by S phi of E is phi of ES star. And this is the appropriate suitable generalization. And then we consider the set of germs, and we define the domain of germ S phi to be equal to phi, and range of a germ to be equal to S which acts on phi. And we get a category. And so we have now two passages. We have a passage from categories to semigroups and back from semigroups to categories. Yes. And my results state that these passages are actually mutually inverse. And moreover, I see what we get in the case of strongly ample categories and what we get in the case of biample categories. And I also consider various types of morphisms. So yes, let me formulate some of these results. So if we have range semigroup, then the category which we construct from it is strongly ample. Its range map is open, and we can define the range of the slice theta s. So our semigroup embeds into semigroup of slices of its category, and actually range map of applied to theta s is just d of s plus. Okay, and so we see pluses. Well, now, very nice connection. Element is bideterministic if and only if its image, its theta s, the slice assigned to it, is in fact a bislice. If S is étal, then R is the local homeomorphism. So we see very, very nice correspondence. And another nice property, if S is étal, so étal precisely means that every slice is a finite join of bislices. I didn't put it to slides, but that is the definition. And in this case, the category of germs étal to D of S coincides with the category of germs assigned to S. Okay, so bideterministic elements suffice to construct the dual category. Well, here I presented two slides with morphisms, but perhaps I need to mention them very briefly or even skip them. My approach to morphism between semigroups is classical, so morphism between two pre-Boolean restriction semigroups is 2-1 morphism, so morphism which respects multiplication and star operation, and we also require that restriction to idempotence, to projections, is a homomorphism of generalized Boolean algebras. And I now specify two subclasses, proper morphisms and weakly mid-preserving morphisms. These types of morphisms are very natural, but I cannot stop on this at the moment. And for topological objects, I follow approach introduced by Bass, Axel, and Mayer, and I introduce the notion of a cofunctor between ample topological categories. So to define a cofunctor, we first define a transformation category. So we have a topological category acting on topological space, and from this data we can construct a transformation category. And after that, when I have two ample categories, by cofunctor, I mean a pair mu f, where f is a proper morphism, and me f is an action of C on D0. It's kind of technical definition, but it's very, very natural. And in our previous work with Lawson, we had relational covering morphisms. But in this case, I argue that cofunctors are, in a way, more natural. The language of cofunctors is a more natural language for describing morphisms. And so here in this proposition, I collected connections of properties of cofunctors with properties of morphisms of semigroups determined by them. So there is very, very nice correspondence. And finally, having described both objects and morphisms, I'm ready to present the main result. Actually, the following pairs of categories with suitable morphisms, actually Varian morphism, we have several equivalences, are equivalent. Category of Boolean restriction semigroups with local units, and category of ample categories, category of Boolean range semigroups, and category of strongly ample categories. And étal Boolean range semigroups are dual to biample categories. first point implies Cockett-Garner duality for monoids, trivially. And also we can recover the duality by Kudryavtseva and Lawson because we have both domain and range operations on the topological side. So if you are interested, please see more details in my paper. So now I tried only to briefly present it, but I mean, paper is long and contains many constructions, and paper is available in open access. Thank you very much for listening.